Yeah, get caught up. But now that we're back, try your best to kind of keep up with this stuff too. But just so you know what's going on when we're in class, okay? But since you kind of backed up, I won't like take any off for like late and stuff, okay? All right. Anyways, guys, I'm gonna do all 6 problems since there's people at home that aren't here to ask questions. Won't take too long. When we're done going over these 6, there is a new post today that's interactive little lab simulation thing on circles, and since we're not gonna have the full period to work on it, I'm not gonna post anything new tomorrow. All right, so just have it turned in by Monday. It's not too long. Okay, I'll tell you a little bit more about it after we go over these. All right, it says in number 12 on page 156, a runner moves at a speed of 8.8 meters per second, rounds a bend with a radius of 25 meters. What's the centripetal acceleration? And this is also the one I told you guys. The second part was just you identifying what specific force is centripetal. You don't have to solve for it, but let's first find the centripetal acceleration. That's going to be a real easy one. It starts by giving us how fast it's going, 8.8 meters per second. And the radius of the bend we're going around is 25 meters. So what's the simple formula we use when we know V and R to find centripetal acceleration? Yeah, first. Exactly. So 8.8 squared divided by 25. And that should be coming out something close to, should be around 3.1. Yeah, we round to 1 decimal point. 3.1. And even though this is, remember, this is a somewhat special type of acceleration that is due to changing direction, not due to speeding up or slowing down. But even so, it still has the same units as acceleration we always have, meters per second squared. This particular example was somebody just running, right, around a turn. And we kind of already used a similar example to this earlier in the week. What would be, it doesn't ask to actually physically find it because we don't have enough information. We just want to identify what would be the force that is causing the centripetal acceleration, hence the centripetal force. Like friction, right? If all of a sudden you're trying to walk around a turn and it turns into a sheet of ice, you're not turning anymore, right? So in any case like that, or like a car rounding a flat turn, something like that we did an example on yesterday, I think it was. It's friction. But another note before we move on to the other problems. If you remember back to the past, once we learned what a G was, 9.8 meters per second squared, when you hear like term G forces, those are actually accelerations, right? And when you accelerate, we learned in the past as well that you could feel like heavier or lighter, right? We did like elevator problems, and it works on other situations with other axes. Anybody play hockey in here or ice skating or anything? No? How many of you have ice skated before? All right. So this would apply to running too, but especially on skates when you could turn very fast. Especially if you're not that great. If you try to do a real sharp turn on ice skates, what could easily happen? Yeah. You'd slip and like almost slide off the turn, right? The blades on the skates, if you're doing a real sharp turn real fast, have to dig in real hard. And if you do it well and don't fall off it, you feel a lot of pressure in your legs. It makes you feel like heavier around the turn because you're accelerating around the turn. Even if you're not physically speeding up, even if you go into a turn at a constant speed, as soon as you start to change direction, you have at least centripetal acceleration due to the change in direction. And that's going to put more pressure on your legs to get through that turn if you don't slide off. And it hence make you feel like heavier through the turn. And, of course, obviously, hockey players, skaters have to have very strong legs to handle turns like that over and over again quickly. All right, moving along, number 13. A car racing on a flat track travels at 22 meters per second around a curve with a 56-meter radius. Find the car's centripetal acceleration, and then what minimum coefficient of static friction between the tires on the road is necessary for the car to round the curve without slipping. This is a lot like the one I did yesterday as an example on the video for you guys. It just rearranges what we know and what we don't know, okay? But actually, and it asks us two things. First, it asks us to find the centripetal acceleration because, again, it gave us how fast we were going, 22 meters per second, and it gave us the radius of the turn, which is 56 meters. So from that, we could use the same exact equation we used in the last problem. And I should get about 8.6 meters per second squared for that. But then it goes on to ask me for the coefficient of static friction necessary to go around the turn without slipping. Now, in yesterday's wording of the problem, it was like finding the velocity was the unknown, given the coefficient to go around safely. And we defined, if you watched the video yesterday, safely going around a turn means not like skipping or skidding, right? And that means if you're not sliding, essentially, we're in static friction conditions from this type of stuff we learned about last chapter. So this is where, once we're asked stuff about that involves forces, we should go to Newton's second law adjusted for circular motion, which just looks like that. What is the centripetal force here? Friction, right? This is car going around turn. So we can say friction, static, equals m times centripetal acceleration, which we already found above, we'll use in our answer. Now, just like yesterday's example, or extra example we did, we aren't given mass, so that might concern you, right? But in a situation like this, if you do all the subbing right, mass will eventually cancel. So the formula for static friction, like we've been using and like we used yesterday, was mu static times the normal force. And that will equal m times centripetal acceleration. And one more substitution. On a flat surface, what is the normal force equal to? Yeah. Right, the weight of the object is its mass times little g, right? So we make that final substitution. And you might remember in yesterday's video I said, I don't care if you make bigger jumps from like here to here of steps, as long as you understand why in your work. Alright. Cancels, cancels. I could solve for mu static now. It's just centripetal acceleration, which we already found above, divided by little g. So that's going to be 8.6 divided by 9.8. And always keep remembering that mu values, coefficients of frictions, should typically be between 0 and 1. So if you would ever get out of that range, I'd probably check to see if I did something wrong. And I get about 0.88. And remember, this is that unitless value that is representative of like the roughness or smoothness between the textures of the two surfaces in contact, the roads and the tires. We okay on that one? Pretty much like yesterday's, just mixed up what we knew and didn't know. Alright, going along, number 14. An airplane traveling at 201 meters per second makes a turn with the smallest radius of the circular path in kilometers. We want to end up converting our number in. That the pilot can make and keep centripetal acceleration under 5 meters per second squared. And just a note, kind of a realistic thing with this problem is, if you're a pilot and you're making a turn, or if you make too sharp of a turn, those centripetal accelerations are greater. Because if you shorten the radius of the turn and still keep a high speed, you'll have a greater centripetal acceleration. And since those types of acceleration mimic gravity, feelings of gravity, then if they're too high, they could be very, very dangerous. And a more kind of common sense thing that we all know, if you're going pretty fast in a car and you go around a turn, you don't want it to be a very sharp turn, right? Because the centripetal acceleration would take a high force to keep you on. And if you don't have that high of a force, the friction only could hold you on so much, you could go flying off the turn, basically. But this one gives us a speed again of 201 meters per second. This time, using that value, we need to find R to keep my acceleration no bigger than 5 meters per second squared, my centripetal acceleration. So, pretty easy problem, again using this formula. But solving it for R, rearranging it, looks like that. Plugging in the numbers, we get 201 squared divided by 5. And that should give us somewhere around close to 8.1. Double check. Well, once we get kilometers. Okay, so it'll naturally come out in meters as long as everything's in meters per second and meters per second squared. So I get out about 8,080.2 meters, but it did ask it in kilometers. We moved 3 places to the left, so that would be like 8.08. We could round that to for kilometers. We got okay on that one? I mean, not much to it. Know the equation, pop in the numbers, right? Alright, 15. Although it's not a car rounding the turn problem, it's very similar. It says a 45 kilogram merry-go-round worker stands on the ride's platform 6.3 meters from the center. If her speed as she goes around the circle is 4.1 meters per second, what is the force of friction, and it gives it away right there, necessary to keep her from falling off? So if you're standing on a rotating platform, what's making you go in a circle is your feet are standing on the platform and the friction between your feet and that. So even if it didn't tell you that there, you should know that. So the mass was given 45 kilograms. The platform's radius is that we're standing from the center is 6.3 meters. V is 4.1 meters per second. We want to know the friction force. So we again go to set this up starting like kind of like one of those turning problems with the vehicle. Starting from here, identifying the fact that the centripetal force is friction. We don't have to break friction down any further in this one though, due to the fact that we're not asked for the coefficient of friction or anything like that. So we just want the whole amount of friction as a force. So, and we could kind of do it all together here. M, and for A, the centripetal acceleration, I could plug in the formula V squared over R and just kind of do it all at once. So that would be 45 multiplied by 4.1 squared divided by 6.3. Run those numbers carefully and we should be getting out close to 120 newtons, it looks like. Like 120.1 newtons. Any questions so far? 2 more down on the bottom. Centripetal force. A 40-gram stone, we need to convert that immediately to kilograms. That'll be 0.04 kilograms. It's on the end of a line of a string, kind of like what I was using the last couple of days, just swinging something around like that, horizontally, horizontal plane. 0.6 meter string, that would be the radius of the circle, at a speed of 2.2. What's the tension in the string? And really, this one is, it might not seem like it, but it's really practically the same problem as number 15. But instead of the centripetal force being friction, it's what now? When you're doing this. What's causing the circular motion? Yeah. What's that? Tension, exactly. So other than that, everything's exactly the same. We start with noting that from Newton's second law, plugging in tension is the centripetal, and subbing in V squared over R for the centripetal acceleration. And it's different numbers, but practically the same work, just for a different named centripetal force. Run all those numbers, and you should be getting close to around 0.32 newtons. One thing we are going to move along to early next week is going into vertical circles. I mentioned that the other day. If I'm keeping this thing at a constant speed in a horizontal circle in a situation like this, at 2.2 meters per second, let's say in this problem, then the entire time my tension is also constant at 0.32 newtons, as long as the radius doesn't change and the speed doesn't change. But that's not true once on Monday we get into vertical circles. Because once I do this, even if I maintain a constant speed here, the tension does change because of how it interacts differently with gravity at different positions, since gravity is on this axis. So that's one thing that'll differ a little bit. That tension won't stay steady at like one in this particular problem did. And finally, number 20. That was the last one, right? A bowling ball has a mass of 7.3 kilograms. If you move it around a circle with a radius of 0.75 meters at a speed of 2.5 meters per second, what force would you have to exert on it? So it literally says you, like you're holding it and making it do that. So in that case, the centripetal force could just be your applied force, right? So M equals 7.3. R equals 0.75. And again, just like the last two problems now, this one's really the same problem. So the third problem in a row we were given M, R, and V, right? But this time the centripetal force is just your applied force that you're making it. You're grabbing it, just doing something like that with it. So that'll equal M times, I'm just going straight to this equation since this is the third time in a row we've done it. It's just applied force there instead of tension or friction. 7.3 is 2.5 squared over 0.75. All the units were good. That thing was meters. And this will be about 61 newtons, something close to that. So most of those are pretty similar to each other, or at least the ones we did yesterday as examples. Any questions on any of them? Okay, as far as horizontal plane circles go, we'll get a review set sometime next week that have a few more, but there's nothing a whole lot different. The only other different ones are going to come early next week when we do those vertical circle ones. All right, since there's no other questions, just before you flip to the assignment that was posted today, where is it? Just showing you the interactive, but if you've paid attention when you've been in class so far this week or been watching the videos when you're at home, this should be a pretty straightforward simulation, and the worksheet that goes along with it should be easily understood if you've been grasping all this stuff. So on this particular one, when you hit start, it'll just map out a circle. A few things we could change are the speed, radius, and mass. Those are most of the givens we were given in these problems, right? And you can note that based on whatever your settings are, this simulation will show you the acceleration. Just remember, meters per second is the same as meters per second squared. Learned that a long time ago. And it shows me the net force involved. Or in other words, really, that's in this particular simulation, the net force is the centripetal force. Whatever it is, we don't really know for sure, but that's the centripetal force. Okay. You can include the velocity vector and the acceleration vector to confirm where they point at any given moment. Turn those on and off. They'll just run through some settings of what you're supposed to do on that and change some numbers up and answer some questions about it. So go ahead and use the rest of the time today to start this. Don't finish it today, continue on it tomorrow, and have it turned in by Monday. Actually, I think I set the due date as Sunday night. So you'll probably, between working on it a little bit now and maybe a little bit tomorrow, have it done. If anybody has any questions while they're working on it, let me know.